All right, it's a great honor to speak at a conference here in Miami in honor of Marjorie Richard's 50 years of mathematics. I actually really do love to read Marjorie's papers. The way they're written is, I think, a model of how mathematical exposition should work. It's not really this kind of interminable build-up of definition after definition, but rather it's a story that you can read and understand. And I try to emphasize to my students, most of the time without any success, that they should follow this model, and I try to follow it myself, and that's quite difficult, but once in a while we manage, and it's always more beneficial to write a paper in that way than in the robotic style that will soon become obsolete due to artificial general intelligence. Sorry. So what I'm going to talk about today, and this is payback for all of you hate bundle people, I've heard enough. I'm going to talk about double groupoids and generalized Kahler structures. What you see on the left is either a 16th century Moorish tile pattern or a double groupoid, depending on how you want to think about it. What I'm going to speak about is joint work with my postdoc, Daniel Alvarez, who is and also my former PhD student, Yucong Jiang, both of whom were trained by Henrike Bernstein, the first as an undergrad and the second as a PhD student at IMPA. And they're both fantastic mathematicians. Yucong is at UIUC at the moment as a postdoc, and Daniel is on the market. And I expect that he will do very well. So I hope that prediction comes true. So generalized Kahler structures, they started with this paper from 1984 by Gates, Hull, and Rocek, physicists. And let me just highlight a few things out of their introduction. So they mentioned right in the introduction that in 2 dimensions, this is for a 2-dimensional field theory, a 2-dimensional signal model, one supersymmetry implies no special restriction on the scalar manifold. That when you're mapping from your 2-dimensional spacetime into your Riemannian manifold target, that's signal models, mapping into a Riemannian manifold, no supersymmetry is no special geometry on the target manifold is needed in order to have one supersymmetry in the model. For the model to be supersymmetric, you don't need anything, just the Riemannian manifold is sufficient. But if you want more than one, then reference number 2 here, notice this is an incredibly pivotal moment in the history of math and physics, in my opinion, is this paper 2, which is a paper of Zunino, where he first realized that if you impose Kahler geometry on the target, then the model becomes supersymmetric. Okay? And that led to everything else, mirror symmetry, Calabi-Yau interest from physicists, everything. So everything, I think, in this current 40-year wave of interest from physicists in what we do is coming from that paper in a sense. But having more than 2 requires hypercahler manifold. Now, these are physicists, so when they say require, you shouldn't take them literally. They have trouble with implication direction. If they say that it's implied one way, it usually means the other way. But that's fine. You learn how to read these papers. So it's not necessary that you have a Kahler manifold in order to have this type of supersymmetry. It's not necessary to have hypercahler. It's just one particular construction. If you have a Kahler manifold, then Zunino tells you how to make the manifold how to make the model supersymmetric. Okay, so what they're doing in this paper, they say they're going to extend previous analyses. So in this paper, they introduce basically a new source of a new type of geometry that will give the same supersymmetry algebra for the model. And they mention here, in particular, they involve complex structures which are covariantly constant with respect to a connection with torsion. In the Kahler case, we have only one complex structure. In this case, we apparently have more than one complex structure, as they mentioned in the plural. And in the Kahler case, it's covariantly constant with respect to Levi-Civita, and here it's a connection with torsion. Okay, and so it's very interesting that kind of, there are certain things they say in the introduction that I am sure they wish they hadn't said. So one of them is this, that they say, the manifolds on our new theories, although not Kahler, possess two commuting complex structures, I plus and I minus. Okay, so they later say in the paper that they don't have to commute, but they thought that at the time that they were developing this paper, they thought that maybe they made a mistake and that maybe the complex structures were supposed to commute, but they couldn't derive it from the equations of motion. And so they went on, they said this, but later, oh, and by the way, the action that they build, they say it has a generalized Kahler gauge invariance. So there's the first occurrence of the term generalized Kahler in their paper. Okay, and so this is the beginning of the paper. Let's go to the end of the paper. These are the last 2 pages. The whole paper assumes that the complex structures commute, right? But they say if we do not assume that the complex structures commute, we obtain a more general class of sigma models with this action that need not admit an almost polar structure. We hope to analyze these models more fully in the future. And they thank, guess who? So I think Nigel told me that they told him about this geometry and he listened to them patiently, stored it in the memory banks, but did not work on it until maybe 25, 30 years later. So it's good to have a good memory. Eat your spinach or whatever helps with memory. What is a generalized Kahler structure according to Gates-Hall-Rocek? It is a Riemannian manifold with 2 complex structures, I plus and I minus. They're usual complex structures. Each of them is compatible with G, but there is no algebraic condition between them. They do not commute and there's no condition on them. Each of them is a complex structure and they need not even be isomorphic. So you could have the same diffeomorphic type with 2 different complex structures that are not isomorphic. Let's say like this, the P1 cross P1 and the second Hertzsprung surface. They're diffeomorphic, but not holomorphically equivalent. They could occur together on the same manifold like this. And the Kahler forms are not Kahler forms. They're not closed. Instead, their DC are balanced against each other in this way. So the DC of omega plus and the DC of omega minus, the 2 Hermitian forms, they balance out in this way. And although DC omega plus is not 0, D of it is 0. And so what happens is that this 2 form gives rise to a 3 form, and that 3 form is closed. And we call that 3 form H, and that 3 form gets stuck here as part of the structure. So we keep track of that 3 form. It's part of the structure. Here I'm just reminding you what DC is. It's the other real operator that you get. It's like I del bar minus del. And I'm reminding you what a Hermitian form is. It's just the contraction of the metric with the complex structure. So this is it. So this replaces the equation in Kahler geometry, which says d omega equals 0. Okay, that's what this replaces. An example. Here's a huge class of examples. Take any even dimensional real Lie group with a bi-invariant Riemannian metric. So for example, I could take the simplest one would be SU2 cross U1. I could take SU3. Okay, these are all, this one is 4-dimensional and this one is 8-dimensional, beloved by physicists. And these are of this type. They both have bi-invariant metrics. And then what you do is you look at the roots, you split them into positive and negative roots, and then you define a complex structure on the Lie algebra by saying that the positive roots are in the plus I eigenspace of this complex structure. And then the negative roots would be the complex conjugate, would be the minus I eigenspace. And then the Cartan subalgebra, which in this case for SU3 is 2-dimensional. You just choose any constant complex structure on that. Therefore, you get a complex structure in the Cartan subalgebra, and it's been extended to the whole Lie algebra in this way. Now you have a complex structure on the Lie algebra. Okay, then you can left translate it over the whole group. You can right translate it over the whole group, and you get 2 complex structures, the left invariant one and the right invariant one. They're both compatible with the metric, but they're not Kahler, of course. It's a group, it doesn't have any H2. But instead, if you take DC of them, They agree up to a sign. They agree, they satisfy this equation. And they define a closed three form, which everyone knows, it's the Cartan three form. So it's a beautiful geometric structure on any such Lie group. So it's, again, I just want to emphasize, this is a real Lie group. It has a complex structure, it's a complex manifold. It's not a complex Lie group, but it's a complex manifold. It's otherwise known as the Hawk surface. And we saw some other examples of this yesterday when we were talking about those non-algebraic style manifolds. They're all, these are of that type. So these are generalized Kahler. Okay. This is very, very important for physicists because they like to take these groups as targets for sigma models. So it's very important that these models have 2, 2 supersymmetry, which is the same supersymmetry algebra that Kahler manifolds give. So that's very significant for them, for building these superconformal field theories. Okay, so more examples. So we have, of course, Kahler manifolds. They're the boring ones, where you take I plus and I minus to be the same, or minus of each other. So in other words, there's 2 ways of embedding Kahler into generalized Kahler, depending on whether you take I plus and I minus with the same sign or with the negative sign. The other example is hyperkähler. If you forget K and you only use I and J, they will both be compatible with respect to G, and they will satisfy, of course, this equation because they're both Kahler. But then what you could do is you could deform these, and a lot of work has gone into these deformations. There's work of Goto, there's work of Hitchin, there's work of mine, where we explain that if you start with a Kahler manifold with a certain type of structure, you can deform I plus and I minus so that they diverge from each other. And they're no longer a Kahler, but they actually differ in an important way. And there's another family of examples where you can take this hyperkähler structure and you can deform the metric in such a way that it remains compatible with I and J, but it breaks compatibility with K, and it fails to be hyperkähler, but it continues to be generalized Kahler. So we have a large number of examples of this type of geometry. It's very flexible in the same style as Kahler geometry. Okay, but how flexible is part of the question of this talk. I want to mention something that is not often brought up. I've never wrote about it, and neither has anyone else, which is that there's a certain kind of Galois symmetry. So if you think of the category of complex manifolds, okay, if you have a smooth manifold with a complex structure, you can always take that complex structure and reverse its sign. And that is a symmetry that the category of complex manifolds has, right? If you take a complex manifold, you can flip it over and you'll get a different non-isomorphic complex manifold. It's very rare that they would be isomorphic. If that's the case, we say that the complex manifold is the complexification of a real manifold, right? But there is this Galois action, right? Algebraic geometers know it very well. It's the idea of how R embeds into C, and it's the Galois action on C as a field extension of R. But in this case, we have 2 of these. Oh, it always does that. And I had the same problem yesterday. So we have 2 Z2 actions where we can flip the sign of I plus or of I minus. Okay, and these equations remain satisfied because omega plus involves I plus, but DC also involves I plus. And so the sign of this term, independently of this term, remains fixed. Okay, so this is a symmetry of the entire system. So there seems to be a Z2 cross Z2 action on the category of generalized Kahler manifolds. And we're going to see that later come up as an important feature. People who are too clever will say, well, why not just flip the 2? Why not exchange them? Right? That seems to be another symmetry. And that is true. However, it will change what you call H, right? Because H is supposed to be DC omega plus, right? And we know that the omega minus 1 is with a negative sign compared to omega plus. So because we're keeping track of H, you're not allowed to exchange the 2 complex structures. That is something that is there, but it doesn't map it to the same class. It changes H. So far, so good. Any complaints or questions?
changing the sign of I plus doesn't change the integral.
No, because in here, we have one I plus feeds into omega plus, and we have another I plus feeding into DC. Okay. All right, so when Nigel finally got around to working on this subject, he didn't realize what he was doing. He was doing something completely different, apparently. I thought he was doing something completely different, and I never even knew about Rocek's obscure paper. It used to be obscure. But when we realized that a certain generalized geometry was giving us a pair of complex structures, and I remember when he asked me, it's amazing that he knew this fact about their original paper. He asked me, do they commute? And I said, I don't think they commute. There's no reason for them to commute. And he said, I remember this paper. And he just immediately went to the drawer, the big drawer that everyone probably remembers where all the papers are, and picked out that paper. He said, look at this. And then, so finally the connection was made. But the idea is the following, that a generalized Kahler structure in the style of generalized geometry is a pair of generalized complex structures. I call them JA and JB. Now, what are these things? These are complex structures, not on T, but on T plus T star. So that we have complex structures on this extended bundle. This bundle has an inner product, of course, because it's T plus T star, so you can contract. It has the split signature inner product. And it also has a bracket, which was studied in great detail by the Weinstein school, Pablo Cervera, Alan Weinstein, and their collaborators. And you can see that in the bracket appears this three form. So the integrability condition of this complex structure depends on this three form. The three form is like background geometry, just like in Jules' talk, where he was talking about how the manifold itself incorporates the three form, and the T-duality is operating at a topological level with respect to this three form. So it feeds into the integrability condition. Both of these are integrable with respect to this bracket. And the important thing is that they commute. They commute and they satisfy a positive definiteness condition. So this is supposed to be like a symplectic structure and a complex structure that are compatible, making a Kahler metric. That's what you should think. That's the idea. That's why we called it a generalized Kahler structure. Now, I kept the first definition on the left and the second definition on the right. So you see the two definitions. We have a bi-Hermitian structure, and we have a generalized Kahler structure, right? And one of my early theorems was that these are equivalent. Why is that? Well, one way is that you can assemble this data. I remind you, these do not commute, these do commute. Okay, but this is on a larger space. So you could think that we just made more space, more room, so that the two things that didn't commute, now they commute because they have more room to commute, roughly speaking. But to be more precise, if you take these tensors and populate this matrix and think of this as an endomorphism of the T plus T star, so this is acting on T, this is acting on T star, and these are cross terms, off diagonal entries. We get commuting operators on T plus T star. That's not exactly obvious. It requires just a little calculation to see that these two with the plus sign or the minus sign, they do commute. On the other hand, if you start over here, you can do a very nice analysis, because since these commute, that means that their eigenspaces decompose according to the eigenspaces of the other operator. And so what happens is here I've plotted the spectrum of JA, plus I, minus I, because this is a complex structure, and the spectrum of JB, plus I and minus I. And so we see that we have four joint eigenspaces, right? I minus I plus I and minus I for both JA and JB. This means that T plus T star splits into four spaces. I've drawn the four spaces here. 1, 2, 3, 4. And the idea is that you can see that because JA is involutive, because JA is integrable, what that means is that the plus I of JA, which I've called LA, that this thing should be closed under the bracket. Okay, and the fact that JB is integrable means that the plus I of JB should be closed under the bracket. But because they intersect in this space should be closed under the bracket. But this is smaller, right? This is 1/4 of the size of T plus T star complexified. And so when you take that L plus and project it down to T, what happens is that you'll get a usual complex structure. You'll get T01 of a complex structure. And then if you take L minus and you push it down to T, you'll get another complex structure. So you see that what's happening is that T plus T star is providing you enough room so that you get one subspace which has a plus complex structure and another subspace which is orthogonal to it in the natural metric, which has the other complex structure. And then the thing that's most tricky to prove is that this integrability condition is the same as this Courant bracket integrability condition on the right. Okay, so this transformation is the main tool that underlies a lot of the advances in the study of this geometry. So let me explain one of those. So if we take this generalized Kahler structure in the version 2, okay, what you notice is that, well, as I said, this L plus, this small thing, if you map it down to T, you get the 0,1 tangent bundle of a complex structure I plus, and similarly for L minus. And it is sitting inside these larger bundles, which I called LA and LB. All the original T plus T star, LA and LB, they all contain a copy of this T01 of I plus, okay? But also we have this bracket. So what that tells you is that if you take any section of T01 I plus, right, you can put it in here, and then by using the Courant bracket, it will act on this involutive subbundle. You just bracket against the rest of the bundle. Take any section in L plus, it will act on LB, and it will act on LA, and it will act on the entire T plus T star. And what that means is that all these bundles get a D-bar operator. They all get a del bar operator. So they all become holomorphic with respect to I plus, okay? And as a result, what happens is that T plus T star becomes a holomorphic bundle. Now that holomorphic bundle turns out not to be holomorphic T plus holomorphic T star. It turns out to be a deformation of that. It's a non-trivial extension of T by T star in the holomorphic category. So we get a holomorphic, what we call a holomorphic Courant algebroid, because it's like T plus T star, it has a bracket, but it's holomorphic. And this thing decomposes as a sum of two holomorphic subbundles, which come from the LA and the LB. And both of these are what are called holomorphic Dirac structures. And the important thing for today is that these are Lie algebroids. Okay, so what is this? So we have a complex manifold. We have a holomorphic vector bundle. The vector bundle has a bracket. It's holomorphic. It has an anchor map to the tangent bundle. So this is an avatar of the tangent bundle, but it's a different bundle. It's a Lie algebroid. So what does this mean? This means that we suddenly realized that on the two complex manifolds in GK geometry, we have this richer structure. What is the structure? It's a holomorphic Courant algebroid with a pair of holomorphic Lie algebroids sitting inside them, okay? And we get the same thing for minus. So these two slides are supposed to be very slightly different. So notice that the only difference is that LB gets switched to LB bar because I want to focus on the minus complex structure instead of the plus complex structure. So LA remains the same because I'm still looking at the I eigenspace of JA, but the B eigenspace is different. It's the lower one. Nevertheless, we can make the same argument, and then on X minus, we get this whole same type of holomorphic data. So this holomorphic data is on X minus, and this holomorphic data is on X plus. This type of data has been studied in the Weinstein school. It's called a holomorphic man in triple, because of the fact that it's very similar to something that occurs in Lie algebra theory. It was introduced by Drinfeld in his classification of Poisson groups for the study of quantum groups. He had a Lie algebra which was split in a sum of maximal isotropic Lie subalgebras, and he called it a Manin triple. And so Weinstein, Shu, Liu, and their collaborators studied this object, and it's called a holomorphic Manin triple. So that's what we have on either side. Okay, so what does this mean for the complex manifold underneath? It means that each of the complex manifolds, X plus and X minus, they have these bundles, and these bundles can be projected to T, and what you get is a foliation. It's, technically speaking, it's a singular holomorphic foliation. One of them comes from A, the other one comes from B. And they intersect, and they get the third foliation. They're all singular holomorphic foliations, okay? And the thing that you get when you intersect them turns out to be a holomorphic symplectic foliation of a Poisson structure, which was discovered by Nigel in one of his papers on GK geometry. It's called the Hitchin holomorphic Poisson structure. So in other words, this Hitchin holomorphic Poisson structure, which is present on any GK manifold, is actually the intersection of two more primitive objects, which are these two Dirac structures making up the holomorphic Manin triple. This happens a lot, actually. Many times when you have natural Poisson structures, they often come together with this enhanced data of a Manin triple. You just have to look for it sometimes, and you might find it. In this case, it's quite significant because we have these two foliations. So let me give you an example, a very simple example. It's this one, it's the Hopf surface. Okay, so we have a generalized Kahler structure on the Hopf surface, as I explained as the first example. This generalized Kahler structure, it has basically two complex structures on the same underlying manifold, and both of them are this one. They're not, as tensors, they're not the same, they differ, but they can be identified because one of them is left invariant, the other one's right invariant. So if you use the inversion, it takes the left invariant to the right invariant one. So there is an isomorphism between the two complex structures, but they are different. And this foliation turns out to be of the following nature. So there are zero-dimensional leaves at Z1 equals 0. These are all leaves of the A foliation. And then this is an open dense leaf of complex dimension 2. And the same thing goes for B, except that its zero-dimensional leaves are here. And then it has a two-dimensional leaf, which is this. So you can see that the intersection of the two foliations gives you zero-dimensional leaves here and here simultaneously. And the Hitchin Poisson structure in this case is very simple. It's given by Z1, Z2, d by dz1 wedge d by dz2. And you can see that this one is invariant under scaling. And so it descends to the Hopf surface as a Poisson structure on the Hopf surface. So here we see that the two elliptic curves where this Poisson structure degenerates, they are disjoint, and one of them is associated to one of these foliation, and the other is associated to the other. It's quite beautiful the way that they split up in this way, according to the Manin triple. So the main question that I want to answer, that we've been trying to answer, and that the physicists have been trying to answer since 1984, is how are the two complex structures related? What is the relationship between these two complex structures? If they're both present, right, and if they're not necessarily isomorphic, what can we say about their relationship? And since we now have this extended data, how are these related? And this is all holomorphic data, and so is this. And what I hope to show to you is that they have a holomorphic relationship. There's a very strong holomorphic relationship that binds them together, and that's all holomorphic. So for Kahler manifolds, that's like the complex structure of the Kahler manifold, okay? But there's something that's not holomorphic in any Kahler geometry, which is the metric. The metric has no holomorphic interpretation. You can change it by dd bar of a function. And so how is the generalized Kahler metric determined? Is there a potential function? Since their first paper, they've been claiming that there is such a potential function that determines these generalized Kahler metrics, and no one has been able to find it. It's only in special cases that we've been able to determine what could this potential function that generates the metric, what could it be? But for the physicists, this is very important because for them, it's very important for the physicists that you have this Kahler metric, because it goes back to Zunino, that what he realized was that if you have this sigma model and you want to write the action of one of these maps, and what he realized is that what you need to do, or I'm starting to use their language, it's not that you must do this, but it's that you can do this. You can actually extend this to a superfield, and then you could pull back the Kahler potential function and just integrate it over sigma. And that is your action. So for them, this very complicated action simplifies dramatically when you have a Kahler potential. It just becomes the integral of a function. And they were convinced that the same would be true for generalized Kahler. And as usual, they are right. It's just that we couldn't figure out what it was. Okay, so those are the main questions. So the rest of the talk is just trying to explain what our resolution to this is. Here's the key idea. It came from my decade-long slog through the literature of the Weinstein School, okay, where one of the objects that they've studied is called a double groupoid. What is a double groupoid? Well, it's like this, that you're familiar with the groupoid, like the fundamental groupoid. You take paths at the homotopy. It's a groupoid. You can concatenate paths. So it's better than the fundamental group. It's the correct thing. You don't have to choose a base point. But now we have two foliations. So what you should do is you should do the fundamental groupoid of the leaves of one foliation, but also do the fundamental groupoid of the leaves of the other foliation at the same time, right? So you get paths up the homotopy in B, paths up the homotopy in A, and then you should also find squares up the homotopy whose boundary are such paths, okay? And so this is, for example, if you took a product of manifolds, you'd be able to do this. You'd have like a fundamental groupoid along X, and the fundamental groupoid along Y, and then you could fill the boundary of the square with a square up the homotopy. So from the point of view of topology, people like Ronnie Brown and his collaborators, they studied these as well. And but what the Weinstein School did was they studied situations where actually this is a symplectic manifold. It has a symplectic structure. And it turns out that both of these are Poisson groupoids. And this is a space with a Manin triple. So what they were studying, and this came relatively recently, and so there's not that much literature on the double groupoid case. What Weinstein really focused on was the study of symplectic groupoids, just simple ones. But what we needed for this problem was the double groupoids, and the basic reason for that is because of these two A and B, these two foliations. Now, I'm saying foliations, and I'm sweeping a lot of stuff under the rug, because these are not really, strictly speaking, only foliations. They are Dirac structures. And so what you really want is these paths to be equipped with a lift to this subbundle, which is this Dirac structure. And that's very important in order to build this thing. So I'm not going to get into that complexity, but hopefully you'll get the idea that the points of this. Okay, wait. Let me simplify the discussion right now. So this is our original manifold. This thing, which I'm calling the groupoid, is another manifold. It's a finite dimensional manifold, Poisson manifold. So is this finite dimensional manifold, and this is a finite dimensional manifold of these squares up to homotopy. Okay, so there's nothing strange here. These are all manifolds, and these are all surjective submersions. Okay, and these are just the source and target maps. So in other words, if I have a point in D, that point is a square like this, and that square has four boundaries, which are these four maps. Okay, it has two boundaries in B and two boundaries in A, and these are paths. Points in here are paths. They're the red and green paths up to homotopy, and they have a source and target, which are these points, these 4 points. Okay, so in case it's not clear, these are just a bunch of spaces with a bunch of maps, and I'm just saying that there is a literature where they are studied. Okay, now we need to now we get into an interesting necessity that has not occurred in the literature on these things. So when you have two Lie groupoids, so here we have a Lie groupoid gx and gy, we know that in addition to groupoid homomorphisms are the simplest kind of morphism you could imagine. Like you would have to have a map from gx to gy and a map from x to y that preserves the structure. We know that for Lie groupoids, there's a more interesting equivalence relation, which is called Morita equivalence. So the way this works is that, so the simplest example of this is where you have, let's say you have a connected manifold X and you choose a base point. Right? Then the simplest example is that you could take the fundamental group of X based at X naught. That is a group, which means that it's a groupoid over a point. Okay? And then on the other hand, you could take the fundamental groupoid of X, which is the path of the homotopy, and this is a groupoid over X. Okay? So it's true that there is a map from here to here, because I can map this point to the base point, right? And I can map these loops into a certain special subgroup of paths. So there is a morphism, but a Morita equivalence is different. A Morita equivalence is a space mapping to both of the bases by surjective subversions in such a way that both of the groupoids act on it. And it must be that this action, okay, is principal and has this as its quotient, and this action is principal for this group and has this as its quotient.
The X is a different one from the other one.
Yes, so what do I put here? I need something that this acts on in such a way that the principal bundle over X. So what you need to put is the universal cover. Okay, and so here what we see is that the deck transformations act on X tilde, giving the principal bundle over X, and then pi1 of X, it says that it says that you can reach from one point of the universal cover to any other point on the universal cover, right? These kind of chords, right? They give the action of this on this, and it just collapses the entire thing. Oops. So that's this what I call or what they called what Weinstein and co called bi-principal bi-bundles. Okay, and of course these are familiar to everyone in the modern age, because this is how we define stacks. You say that if you took the quotient of X by Gx, that would define a stack, a differentiable stack. And we say that if these two groupoids are related by this notion of equivalence, that means that that's the equivalence relation that we use in order to identify the stacks. So the stack of this groupoid and the stack of this groupoid are the same stack. They're isomorphic stacks as a result of the fact that the groupoids are Morita. So this is a very useful and important idea, this Morita equivalence. Now, on the right-hand side, what do we see? Like for double groupoids, you could kind of think of double groupoids as groupoids in groupoids, but in two ways, right? You could think of this as a groupoid over this, or you could think of this as a groupoid over this. So it's like one of those really irritating menus, like 4 cheeses and 3, something like that. So two groupoid structure, yeah, it's a double groupoid. All right. And because it has this horizontal and vertical groupoid structure, what it means is that there are different types of morphisms. There are horizontal morphisms in which you have a Morita bibundle in the horizontal direction, and I call those 1-0 morphisms. And then it also has vertical Morita equivalences, which I call 0-1 morphisms. Okay, and instead of having a single space, you need to have a groupoid for this groupoid thingy to act on. So, here we have something in the middle with 2 maps. The thing that's in the middle here is a simple groupoid, and it has 2 maps to the sides of this double groupoid and this double groupoid. So this red thing represents a horizontal generalized morphism between this square and this square. And this green thing represents a vertical generalized morphism between this square and this square. Okay, so there's two types of morphisms. What does this mean? It means that it's a higher category, right? It's a category that has 1, 0 morphisms and 0, 1 morphisms. So it's what you might call a double category. I'm talking about the category of double groupoids. Okay. Okay, and you could try to take, you could try to do the same thing that we do with groupoids, which is to define stacks. This would be double stacks, or if you wanted, they would be examples of two stacks. But here, the way that they're being presented to you is preferring to be given this double structure. So it's a double stack. Anyway, so we seem to have this higher categorical structure. All right. So, okay, so why am I talking about these groupoids and so on? Well, the reason is because you see the fact that we got, you see, when we were analyzing the plus complex structure, we used this diagram. And when we're using the minus complex structure, we use this diagram. And we use the same algebroid, the same plus I eigenspace of JA to define A plus as we did for A minus, okay? And what Yucong did in his thesis was to show that this fact, the fact that we obtained A plus and A minus from the same space means that, that the double groupoid integrating this Manin triple and the double groupoid integrating this Manin triple have a horizontal Morita equivalence like this that relates A with A. A plus is Morita equivalent to A minus. These are now groupoids, and these are the double groupoids of these things. So the idea is that, because of the way that they were obtained, it turns out that there is a holomorphic relationship between this and this. And that holomorphic relationship is the existence of a holomorphic groupoid in the middle here that relates these two holomorphic double groupoids. Okay. And the fact that we got B plus and B minus from different subspaces means that we cannot say that this B minus and this B plus are directly related in a holomorphic way. We have to go to the complex conjugate of this plus space. So we need to take the plus stuff, conjugate it completely. So now we use the Galois symmetry in the category of complex manifolds. We get this other holomorphic symplectic double groupoid, and we see that there is a vertical morphism between D minus and D plus bar. Okay, this is the thing that confused me for at least a year. Maybe it's embarrassing, I shouldn't have said that. Anyway, the point is that we apparently need to copy, in order to understand the holomorphic relationship, we need both the I plus and the I plus bar, which is another complex manifold in the picture. Right? Okay, so, and as a result of this, okay, it turns out that, well, okay, as a result of this, what I could do is I could take this top part and complex conjugate it, and it would give me something down here because I haven't said anything about X minus bar. So I could put that in, and what you would get is this X minus bar, and this would be complex conjugated here, and this would be complex conjugated here. So now I've just reflected the entire diagram that I drew before, and I get this square, the boundary of a square in this double category. Okay, so what am I talking about? I'm basically saying that there are 4 holomorphic symplectic double groupoids. When I say symplectic, what it means is that the big spaces, these Ds, they are all holomorphic symplectic manifolds. Okay, and they are related by a square of generalized morphisms with Morita equivalences like this. Okay, and the final piece, and this took us a while to figure out, but the final piece of generalized Kahler, if you want to get an equivalence, you need to realize that this kind of loop that we've constructed has a filler. And this is a higher morphism. This is I've drawn it as a double arrow. I've labeled it as 1, 1. It's like a 1, 1 morphism. So the idea is that this double category is like a chessboard or something planar, right? You can go in one way and you can go in another way, and you can make you can make paths in this double category, paths of morphisms. And what we've obtained is a holomorphic loop in this category. And then the point is that there's a filler, there's a contraction for that loop. And that contraction is represented by a space, C. That C is a holomorphic symplectic manifold. Okay, it's not a groupoid or anything, it's just a holomorphic symplectic manifold. And it's equipped with maps to the bases of these groupoids, 4 of them like this. And the idea here is that because this maps here and it maps here, this line here becomes a diagram of this. It becomes a simple Morita equivalence between W groupoid and its complex conjugate. And similarly, at the same time, it becomes a Morita equivalence between these two things. I know it starts to look like religious beliefs, I'm sorry, but all these coincidences occur, okay? And so this thing is a holomorphic symplectic space in the center, okay? So this is the data that we have so far. And now the question comes, well, we saw that there was you see, like the relationship between this object and this object is complex conjugation. And so everything at one end of the diagram is complex conjugate to the opposite part of the diagram. So like this. And so what this ends up meaning is that C inherits an anti-holomorphic involution. It has a real structure, this C turns out to have. So this C inherits a real structure. So again, this space, which, let me just tell you the dimension. So if the dimension of our original complex manifolds is n, then these two will be double, and these will be double that. So this is 4n dimensional, and it's holomorphic symplectic. The 4 extreme points, those are all holomorphic symplectic, and the center is holomorphic symplectic. Okay, those are the only symplectic manifolds in this, and they're all holomorphic symplectic. But this one has a real structure. It's the only one, it's the only space that has a real structure in this diagram because it's in the middle. So we can look at the fixed point set of that real structure, and what we get is a real symplectic manifold, which I call the symplectic core of the whole diagram. And this has twice the dimension of the original manifold. Okay, and it maps, you see here, it maps to X, but it also maps to X bar. And similarly, it maps to X plus, and it maps to X plus bar. And that means that actually these two maps are the same. These diagrams commute in a certain way. And so what that means is that this symplectic core has 2 maps to the original, to the 2 complex, sorry, I'm getting too excited. It has 2 maps to the real parts of these 2 complex manifolds. And the last piece of structure, which is the generalized Kahler metric, is that it's a Lagrangian bisection, a Lagrangian submanifold of this S. So inside that S, there is a Lagrangian submanifold that is a cross section of both of these fibrations. And that Lagrangian is the generalized Kahler metric in the GK class. Everything else is holomorphic. The only non-holomorphic data is this Lagrangian submanifold. And so there, because it is a real Lagrangian submanifold, it can be locally described as the graph of a function. If you choose Darboux coordinates, it has a generating function. And so we finally understand that this GK metric can be described by a single real value function locally, just like in the Kahler case. So the way that I look at it is that all of this holomorphic data is somehow classified by finite dimensional data. You could think that it's classified by cohomology. It's like the complex manifold and the Kahler class together. It's a finite dimensional amount of information, right? The only difference is that instead of in the Kahler case, where you have a Kahler class, which is a class in a linear space, this cohomology is really, it's a class in groupoid cohomology with coefficients in some non-abelian space. So the point is that the Kahler class in this case is a non-abelian type of object, and it's a point in a modulum space rather than a point in a vector space. Yeah, but it's still finite dimensional. Once you have fixed that moduli, you fix this diagram. And then you go into the core and you find this real Lagrangian submanifold, which you could pick arbitrarily as long as you satisfy this open condition of positive definiteness. But apart from the positivity, you could choose it arbitrarily, and that will give you all of the GK metrics. And so that gives you your C infinity degree of freedom. Okay, sorry, I know that I went a little bit fast, but I wanted to give you a picture of what this long sequence of connections finally led to. So thank you for your attention. The credits go to my two collaborators, Yucong, Jiang, Daniel Alvarez. And I have to say that a lot of the ideas really came from reading the papers of these two people, Pablo Chavera and Enrique Bernstein. So I thank them as well.
So, what are the choices in this, setup? I mean, it's like the, as you explained, the original picture for Kahler was the symmetric integral, but somehow the ambiguity in the choice of the Kahler potential disappears because of the symmetry.
Yeah.
Is there an understanding of this in the physics language as the choices that are made here disappear under the integral?
Yeah, so, well, okay, this part is still in progress, which is why the paper is not finished. But the funny thing is that, well, okay, so I'll answer briefly, but I'll tell you what I know. So the thing that's interesting is that, you know, because of the presence of these groupoids here, these double groupoids, there are inner holomorphic symmetries of these things locally. Things like, you know, any group has like the inner conjugation action. So these groupoids have a group of inner symmetries. Actually, it's a two group, but who cares? It's a group of symmetries. And those are holomorphic symmetries. So they are symmetries of this diagram. And therefore, if you have a Lagrangian submanifold, you can act on it by those symmetries. And there are different types because they could come from here, or they're complex conjugates. All right. So this means that the symmetries, they seem to be of different styles, depending on where they come from in this diagram. All right, and if you look in the physics literature, you see what they did in the physics literature is that they took, you know, the reason that they had so much trouble is because what Rochek and the others were doing is that they were trying to choose coordinates that were adapted to these foliations. So they chose what they call twisted chiral fields, and semi-chiral fields. The semi-chiral fields were like Darboux coordinates along the symplectic leaf. And then the other chiral and anti-chiral fields were like coordinates along A normal to sigma and along B normal to sigma. So they chose coordinates like this, which of course you can't do since this is a singular foliation, but you can try, right? And so what they see is that if you look at the freedom for their Kahler potential, you'll see that they allow like holomorphic functions of the semi-chiral, or an anti-holomorphic function of the twisted chiral, or something like that. So there's a selection of different types of holomorphic functions of various fields that can be used to move that K around. And that corresponds exactly with the types of inner symmetries that you get from these different sources. So, you know, eventually, what we should do, and that is a tall order at this point, but what we should do is we should really take this whole picture and bring it back to physics. Because what this means is that if they would write their theory as maps into this thing, I know that they would be horrified at this idea, but it's not so crazy because they do gauged theories all the time. What it means is that you map into space on which there is a big action, and instead of mapping into the base, which is too complicated. So the idea would be that if you map it into C, let's say, with some boundary conditions along this core and along this Lagrangian submanifold, you might be able to get a much more coordinate-friendly description of their model, and one that doesn't use those twisted chiral, semi-chiral fields. Hopefully we can do away with that in some sense, or at least enhance them, you know.
Coming back to one of the first examples that you showed, the hypercable, in which you choose two structures and you deform. I know you had enough of Higgs bundles, but can you perform this in the motility space of Higgs bundles? And if
Yes.
so, what is the meaning of that?
Yes, there's a large source of generalized Kahler structures on the moduli of Higgs bundles, as there is on any hyperkähler manifold. I don't really have anything. Actually, I don't have anything particularly intelligent to say about that. However, okay, what I could say, which is maybe a little interesting, is that in their original paper, they keep talking about, see, they talked about n equals 2, but they also talked about n equals 4. And what that means is that if you do the same, so their idea was they looked at what Zumino realized. They said, oh, Kahler implies two supersymmetries, hyperkähler implies 4. And what they said was that you could deform that, and it could become generalized Kahler and generalized hyperkähler. Okay, so the idea is that hyperkähler, in the same way as what I'm talking about here about Kahler, hyperkähler is just one of the possibilities. There is something called generalized hyperkähler. And the only place where we have seen that actually being used in an interesting application is in a paper of Daniel Huybrecht's, where he was studying the moduli space of K3 surfaces, the complexification of K3 surfaces. So he understood that the extended Kahler moduli space of physicists is really a space of generalized hyperkähler structures on the K3 surface. And so besides that, I haven't seen anywhere where this has been picked up by mathematicians. And so there is this world, I don't know how big or how small it is, but there is this scope for these generalized hyperkähler structures. And they are also characterized by having this 3 form, which means there's a gerb in the picture. So if you have something that looks like a hyperkähler manifold, but it has a 3 form, and it's not quite hyperkähler, then maybe there's a scope, maybe there's a possibility that it could be one of these generalized hyperkähler structures. That's all I can suggest, but yeah, it's an interesting question.
So I'm not sure what was the speech about Alvarez and also.
I'm talking about his 2005 or 6 paper about the space of generalized Calabi-Yau structures on K3 surfaces, which corresponded to a well-known moduli space in physics. When they were talking about mirror symmetry on the K3, it got enlarged, and so he was explaining.
What's the dimension?
You're asking me to remember something that I don't remember.
The question is, isn't it obvious that this is just the whole functional homomorphism, the right category?
Yes, that's right.
So it's not him to be given any credit for anything, but for that as well.
Well, no, I mean, this was very well known in the literature before Huybrecht's, but he identified the points in that moduli space as generalized Calabi-Yau structures, metrics on the K3. It was a different interpretation given to the same moduli space. It's all right. This is, we could discuss later, but it's, I'm just pointing out one space where 4,4 was seen. Otherwise, I haven't seen any other examples.
Any other question? Let's take my way.
Thanks.